Continuing on to second part of lecture 7, we are going to talk about resin transfer molding. So what is the resin transfer molding process? It is taking a dry reinforcement in a closed mold with wet thermosetting resin under pressure. So you push the resin inside a fiber preform that is held inside a mold typically. Uh, so typically, what is the how do you compare that with other processes, other composite manufacturing processes? In this case, you would get about 2 to 8 parts per hour. Whereas if you have a spray up type of a part, you would get about, maybe it would take about 1 part per 2 hours. If you had injection molding or sheet molding compound that you would take and press it into a mold and throw out the components, you can actually make 30 parts per hour. But the issue is that you won't be able to get continuous fiber reinforcement in the case of sheet molding compound or injection molding. You have to have chopped fibers. So that's the advantage. So you can get better parts and better surface finish with the case of resin transfer molding. So here again, similar to other processes, you can use different kinds of fiber types, different types of forms and preforms. So you have to pre-shape the reinforcement into a particular form. So you may have to mold it, or um, you will have to uh, wind it, or you will have to kind of put it together using a winding machine. So a stitching machine, you have to stitch the whole preform together before it is put inside the mold. And then you have to compress the fiber preform so that denser the fiber. But the problem is that if you have a very dense fiber preform, then it will not allow the resin to be infiltrated or impregnated that easily, which means that you will have to have a very low viscosity resin system. And the fiber orientation also is important here, because the resin will flow faster along the length of the fiber rather than across it. And then if you have multiple layers or plies, it will impede or complicate the resin distribution. So if it is very closely packed together, it won't wet all the fibers. So there are a few issues with that, and you have to make sure that those issues are taken care of. Here again, similar to other processes, the polyester is probably one of the earliest ones that they tried, wine luster, epoxy, and things like that. And now there are more high temperature resins being um, molded using the resin transfer molding approach. So what are the desired resin characteristics? First of all, it must remain liquid um, prior to the injection. Then it must impregnate the fiber preform quickly and uniformly, and then it must gel as quickly as possible so that it doesn't flow out, and then it should possess sufficient hardness to be demolded without distortion. So low viscosity is definitely critical, but low viscosity resin means you need less pressure to achieve the adequate wet out. And the injection temperature should be as close as possible to minimum viscosity to ensure preform impregnation. But the higher the temperature, the faster it will cure, so you will have less pot life. So you have to have a good resin curing agent mixing equipment. Typically you need low injection pressures. So you have piston type of displacement pumps, and you have to have accurate metering of the resin system sent through flexible hoses to a mixing head. And that mixing head will then blend the resin and the curing agents immediately prior to injection. And typically these are motionless mixers, so that if it shakes and things like that, then you're not going to get good accurate parts. So these mixers are available in various diameters and lengths to suit a variety of resin viscosities and fillers. So sometimes you also add fillers like chalk fibers and things like that into this. So you may want to do that also, or you may want to add fillers that will take up um, the the um, the reduction in volume or the shrinkage in volume as the resin is being cured. So suppose you have an epoxy resin, you may have about 10% volume shrinkage. So sometimes you may want to add some fillers to take up that uh, shrinkage, so that you end up with a good uh, final part with no voids at all. It may also be necessary to control the resin temperature throughout the injection system, because if you have differences in temperature, you are going to have differences in volume shrinkage, differences in curing, etc. So you need to control that, and the remaining material must be recirculated continuously through the pumping mechanism, so that you are not going to have any least you are going to have the least wastage as possible. So these are some of the aspects of the mold design. I'm not going to go too much into detail about that. And the other thing is that the resin transfer molding process may or may not take place under vacuum. There could be some air entrapment taking place, but um, you have to take that into account. So the resin will push out the air and not so this doesn't typically go into a vacuum typically. And then once it is done, you pinched off the vent ports, and the internal pressure causes the inlet check valve to close, and then it will cure, and then you can remove the part from the part from the mold. So what are the critical issues for the RTM process? First of all, you need to control the infusion rate and flow front of the resin, so that the resin will infuse into the fiber preform evenly and completely, and before the gelling process starts. Typically, the resin is injected into the center of the part, and so that you can minimize the distance that the resin must travel. And then you must take care that the reinforcement does not move during the injection process, so that the fibers don't move to one side and you have resin rich pockets. So what are the advantages of the RTM process? First of all, it is a closed mold process, so there is typically no air entrapment if you are going to properly design the tooling preform and the resin. And once it is well defined, you're going to get very repeatable properties, very repeatable part dimensions, and very repeatable um, process itself. And it allows very high volume, fiber volume fractions, and your design can incorporate damage tolerant features. So you're not going to have very sharp edges and things like that. You can take care of all that during the process itself. And you can incorporate cores, ribs, and inserts, and typically the tooling costs are less than the compression molding type of a process. The I'm not sure that I would say that this is a high production rate process, but it is a medium production rate process. So what are the disadvantages? Disadvantages are that the preparation of the preform could be a labor intensive process, and process waste might be high, and uh, you may, because the it's only fiber, you're going to have some amount of issues with respect to so the fiber could just slip off the mold, so you have to make sure that you have to tie up the mold and you have to tie up the preform. But sometimes you may be able to overcome that by having a mildly pre-pregged type of a preform. So you may want to do that. But sometimes uh, that is not always possible. The preform may have to be oversized, and also you need to sometimes it may have to protrude from the tool edge so that there is a escape route for the air and the excess resin that is coming out of the mold. And there could be, however careful you are, there could be some movement of the reinforcement, and sometimes you also cannot control the resin uniformity very easily. So sometimes you will have the radii and edges will tend to be resin rich because it reaches that place first, and then it is not a good process. So there are certain issues that you have to take care of, and as the part consolidation increases, if your part is has to be scrapped, then it can lead to high losses for the manufacturer, and which means that the replacement cost to the consumer can be significant. So here I have the YouTube videos. You could probably look into that. Please let me know if you are able to access those. Okay. So the next one is reaction injection molding. It is a variation um, of the injection molding process itself. And in this case, you have two highly reactive liquid monomers brought together in a mix head and immediately injected into a heated mold under low pressure. And there it reacts and forms the final part. So there could be fillers also, like chopped glass, carbon graphite fibers, um, and or you can also have the reinforcement placed into the mold before injecting the reactive liquid monomers. So typically it will react after the part is injected. So what are the common resins? Polyurethane. The other one is called DCPD, or dicyclopentadiene, and there is I think Teline website should be able to give you that. So if you go there and see that, you should be able to see some examples of the reaction injection molding process. So here again you have there are a couple of different variations um, of the reaction injection molding process. First one is called RRIM. The second one is called SRIM. So these are different variations. So please go in and look it up if you are interested in this more. So in this case, you have to have what are called date tanks and metering cylinders. So these are just aspects of the RIM process that you need to worry about. Again, a lot of details here. I'm not going to go into detail, that much detail. So please read through that if you are interested. And the final aspect is curing and demolding. So typically the components will react and gel within 2 to 10 seconds from the start of injection, and then the mold will remain closed for a period of time, so 30 to 90 seconds. And then you have what are called knockout pins, and knockout pins are something to push the part out of the mold, and those are typically hydraulically operated or pneumatically operated. That helps in the demolding process. And then or if you have small flexible parts, you may also use a rubber spatula to pry the part or insert an air nozzle and blow it off. So typically for most resin formulations, these parts are post-cure. So here again I have listed the advantages and disadvantages, and these are listed here. The next variation of these is spray up, which is one of the most common methods of composite preparation. So if you have a boat or something like that, a boat mold, or like a transportation component and things like that, you may want to, this is typically the process that is used. So you have continuous fiber rowings fed through a chopper, then it is cut to predetermined lengths, and then it is propelled into a resin stream, and they are continuously deposited simultaneously on the mold. And then you also want to roll it by serrated rollers, or you may want to or you may also have automated processes, and these are typically processes where the fibers may not be continuous. So the advantages are that this is a rapid layup, and you can fabricate large complex shapes where forming and fitting of the mat or fabric would be difficult. So here again you have e-glass rowing and polyester resins. So these are typically the resin systems that is used, and you have a base resin, catalyst, and accelerator in the resin system. So these are the components used in that. So you have a pump, you have a pressure pod, and you have a chopper, you have various air regulators and gauges for the control, and then you have a compressed air source. So you externally mix the resin system, or sometimes you may also want to do, you may also do internal mixing of the resin and the catalyst. And then it is air atomized, so which means that the shop floor can be a little messy, and the shop floor has to be very clean, and people have to have extremely good protection devices, protection equipment, in order to protect them from the air that is being air and the moisture, air and the atmosphere that is in the shop floor itself. You have to be careful about that. This is the description of the choppers for the fibers, and these are some of the considerations for selecting a spray up system. So what is the fabrication process? You have to calibrate the gun, the spray gun, and you need to make sure that you have a specific weight, because these are components where the wall thicknesses have to be accurate, the weight of the component has to be accurate, because otherwise your quality control is not going to be that good if you don't do that. So that means you have to make sure that you are going to be spraying a specific volume within a specific time, and everything is automated and everything has to be controlled. And typically the gun head is about 1.5 feet to 2 feet from the mold surface, and most outputs and operators will maintain about 0.05 inches in nominal thickness per pass. So best laminate is you pass one time, you roll it out, you gel it, and then you continue it again, and then you roll it by hand with a serrated roller to remove the air, compact the fibers, and smooth the surface, and then you do it all over again. So that, and then the curing is similar to a wet layup. Okay, so that finishes the manufacturing processes, and now we will talk about tooling in the next section.